All right, good afternoon. My name is Ali Kujuri. I'm an adjunct professor at the Engineering Science Department and also one of the organizers of this lecture series. On behalf of the department and the School of Science and Technology, I would like to welcome you all to this ninth lecture for this academic year, and also, believe it or not, the 84th lecture of the series since 2006. Let me also thank Agilent Technologies for sponsoring this lecture series since the start. Well, this month is special for us, and the Sonoma State University. Basically, the Sonoma State University honors women of character, courage, and commitment in celebration of Women's History Month. And for that, our department is also celebrating this event, and we have invited our guest speaker, Ms. Julie Silk from Agilent Technologies for her accomplishment as a great woman in the community here. Before I start my introduction of Julie, let me mention that we're going to have 3 weeks from now, that is on March the 27th, a talk from one of the professors at California State University, Sacramento, by the name of Dr. Tom Matthew. He is the chair of Electrical and Electronics Engineering, and the title of his talk is CMOS, that's the complementary metal oxide semiconductor comparators, basic circuits all over again. Another thing that I would like to say is that we have ordered pizza, which is going to be here. That's the good thing, huh?
That's why they're here.
Yeah, it's going to arrive at 5:30 right after the lecture. Ms. Julie Silk is the Environmental Compliance Program Manager for Electronic Measurements Group of Agilent Technologies. She has had a focus on printed circuit assembly design, quality, reliability, and supplier development. She has a Bachelor of Science in Chemical Engineering from the University of Washington and has worked for Hewlett-Packard and Agilent Technologies for over 30 years. A recent graduate of Leadership Santa Rosa, she also is dedicated to encouraging young women to enter engineering fields through Agilent's Introduce a Girl to Engineering Day, and as president of the nonprofit Expanding Your Horizons at Sonoma County. So here is Julie.
All right, thank you all for coming. So my role as Environmental Compliance Program Manager, I'm working toward meeting a requirement from the European Union to get rid of lead, also mercury, cadmium, and a few other things, but the main impact that it's had to our products is getting rid of lead, because the most common solder that we've been using is tin lead solder. So now we're using a solder that no longer contains lead. So anyway, but what I'm going to talk about here is failure analysis and failures in electronics. So how many of you know anything about electronic products, instruments, that sort of thing? Printed circuit boards? A few of you, okay. And you know how they're made? No? Yeah? Okay, good. Well, I am going to cover that because I know a lot of people don't know that, so we're going to have to go backwards a little bit there. But reliability is something that's of great concern to us. It's a big key to customer satisfaction. You certainly don't want something to break right away after you buy it. And with the stuff we make at Agilent Technologies that we design there, it's very expensive. And so certainly our customers want it to last a long time. I'm going to cover printed circuit board construction. I have some materials I'm going to pass around, and some stuff I'll probably wait till later to pass around or to show, like after my talk. The printed circuit assembly processes. I'll talk about some failure analysis techniques and the metallurgy of solder joints. A lot of this is stuff I did not learn in school. As you will find later, is what you learn in college helps you to learn and gives you some groundwork, but what you actually do in your job is often learned there from the other experts around you. So I'm going to show you some printed circuit failures and talk about the ways that we avoid those failures. So we have design rules, acceptance criteria, workmanship guidelines, a whole bunch of requirements that allow us to avoid the failures, hopefully before we even have them, and sometimes we make changes after we find failures. And then I threw in some how these lessons reflect on life. Okay, so this is an example of one of our products. It's filled with printed circuit boards. So the printed circuit boards look like these things. And because ours is test equipment, they need to work better than the products that they're testing. So they're used to test things like cell phones. So we have cell phones like this. And I'll pass around a board that came from the cell phone. You just keep these things circulating around. And I'll send this one around too. So you can see that there's lots of little parts on here. It's usually in some kind of housing for our stuff that's at very high frequency. We need to keep one part of the circuit from talking to the other, so they're usually enclosed in these clamshell shields. And we have a lot of them in there. So any part on one of these, and we can have thousands of components in a product, any one of those can cause the entire product to fail. So it's very important that we keep our failure rate very, very low. So this is an example of some of the circuit boards. I don't think there's any of the ones I actually passed around, but you know, again, there's connectors, there's little parts all over, there's different compartments that keep, again, the signals from talking to each other. And again, if we have any failures, then it's very serious. And what's worse is if we have a failure that we actually ship and it fails in the field. So that's the main thing that we try to avoid. So in order to understand some of the failure mechanisms, I have to go to printed circuit board construction. So here we have a laminate core. So the PCB laminate it's a glass weave that's impregnated with resin, and then it's clad with copper on both sides. And then an image of circuitry is applied, and the copper is etched away so that you get trace layers. Trace layers here, and you get, it takes a while to warm up or something, ground planes there. And then we stack all these together, our fabricator stacks all these together with this layer of half-cured laminate that allows it to squish around the traces during the cure process. So these are put into a stack. They're pressed at high temperature and pressure. The resin oozes around the cracks. It cures. And then after that comes out, then they drill the holes. They plate copper to connect the layers. And then the external layers are imaged and etched. And you end up with something that looks like this. So here you have, I think I'm going to use this one.
This one also. Yeah, you can use that one.
That's better. Okay, so here's the holes. They're plated so that all these layers are connected to each other. My graphics aren't great, but there's the little pads here that are for where the parts go. So when we attach the components, there's a slurry of solder beads and flux that we call solder paste, and it's applied with a stencil. I have an example of that I can pass around too. And then it's all melted. So it goes through an oven, it heats it up to around 250 C. It's pretty hot. It melts the solder and forms a solder joint. So that's the manufacturing process for a printed circuit assembly to make the things like I'm passing around. So here's an example of defects. So here we have a warped, slightly warped board in the frowny direction, and we have a very warped package in the smiley direction. And what you have then is opens, total opens here. You have an open that actually pulled the paste off the pad. You have another open here. You have a stretched joint, so that solder is stretched enough that it's probably not as robust as it should be. You have here a bridge, so it squished the paste together enough that it connected, and you have a short where you're not supposed to have one, so that's not good. And then there's a defect here called head on pillow. So here's the head, there's the pillow, and it never actually wetted. So this is a representation of what's called a ball grid array, so it's balls of solder attached to the part, and this ball did not actually wet to the paste, and so that means that you don't have a metallurgical joint, you just have a physical connection, and those are the absolute worst kind of things to have, because what happens is they're connected now, and a few thermal cycles, on-off cycles later, it disconnects, and so it fails in the field. So those are the sorts of things we really want to avoid. Something like this, we'll find it right away. Something like that, we'll find right away. This one might have a short life. I'm thinking that would have a short life. But this kind of thing is really bad. It'll have a not so long life and not at all long life, and our customers would be very disappointed. So I want to talk a little bit about the analysis methods, how we detect the failures, how we investigate them. So we have high power microscopy, several different kinds. It can be lower or higher power. We're able to see then the component leads, the solder joints. Here's the circuitry on the board, and we have some kind of weird thing here, so we can go a little higher in magnification. And what we have is part of a fly body. So this is probably not a good thing. It could be that it's conductive. It could be that it's just going to look bad if somebody else looks at it very carefully. But this is the sort of thing we can find with our microscopy. The other thing we do a lot of, and I'm going to show a lot of these in this presentation, is cross sections. So for this one, there's a board here. This part has been cut out. It's been sliced and put into a puck of resin, and then polished, very carefully polished so it's very smooth, and then put into a scanning electron microscope so that we can see it at very high magnification. So you see here the lead of the RF connector. You have ground plane connections on several layers. And you can see what's going on. You can see, kind of see, it's probably hard to see here, is there's a copper layer that connects from the top of the via to the bottom and to all of those layers. So like I say, I'm going to show you a lot of these of different kinds of parts, because it's a very helpful way to see what's going on. Because what we have here is the solder, and that's what connects everything together. All right, one of the other things we use along with the scanning electron microscope is energy dispersive X-ray spectroscopy, or EDX is what we typically call it. And with this one, you can detect the elements that are in this cross-section. So you have, this is a solder joint. There's nickel plating down here. There's probably some nickel plating up there. And you can take a line and see, or take like maybe this one and see what exactly is in there, and figure out then what constitutes that exact metallurgical species, what is actually there. Because you'll have different layers of materials, you'll have different, it's not a uniform thing, a solder joint. It's not all tin or all whatever it's supposed to be. There's intermetallics that are in there that have separated out. It's sort of like if you envision like granite material, right? Granite has the main kind of material, plus it's got all these little nodules in it. That's a lot what a solder joint looks like. So this is one where they've taken a line scan across like this. And so you can see there's copper, there's a line here for nickel, so that's the nickel plating layer that's on there. There's some gold. Let's see if I got this right. So I guess gold is down there. You have some other copper here, and then you have some tin, so that's the solder joint. And you also have, they hit a silver nodule there. All right, another method is X-ray. So this is an X-ray scan picture of another ball grid array. So these are those balls that are attached to a part. And what you can see metal only. You can't see plastic because it's invisible to X-ray, and different kinds of metal will show up differently. So you can see that you have solder here is the really dark stuff because it's a denser metal. The thin copper plating is a paler color. And then you can see here that we have voids in those solder joints, so there's big gas bubbles that have frozen into the solder joint. And we also have bridges, so this is where they've conjoined together and have formed shorts where we don't want them. Okay, the other method is die and pry. So this is where we have something that we suspect has cracks in it, but we can't see it. So what we do is we soak it in this dye that penetrates into those cracks very well, and it has a color to it, so usually it's red. So it penetrates into those cracks, and then you let it dry. And once it's fully dry, you rip the part off, and then what you can find is where there is dye where there shouldn't be. So this should all be nice and clean like this, and these over here are red. So we know that there was a crack there. A lot of times we don't see an electrical failure with a defect like this. I'll talk about it later. But where we have fractures, though, and eventually those will fail electrically. So, but obviously this is another one of those very destructive tests. So it's usually just used in experimentation. Okay, so I want to talk about failures. I mean, I gave you a little preview, but the raw board itself has various failure modes that it can have. And I think I need to go over here for this. Okay, so during a heating cycle, like during reflow, so this 250 degrees C that it goes through to melt the solder, there's a lot of swelling, and what you have is I'm going to talk about coefficient of thermal expansion a fair amount, but what you have is a different coefficient of thermal expansion for the plastic than for the copper. So as you can see it going through this is the plastic expands more than the copper, and that puts a lot of strain on the copper. And you can have, okay, so you can have a lot of bending at areas like this, and you can have fractures in here. So this is a really common place to have fractures, is in these kind of areas. Or you can have it stretch so much in this direction that you have fractures through the copper in the barrel. So that's an indication that you have too high of an expansion, or you've gotten the board too hot. So here's a lot of different, an illustration of all the different places where you could have a failure, and this is one that we actually had, where it expanded so much it bowed this copper up. It should be actually flat all the way across. It bowed that up, and it actually separated between the wall of the hole and the copper that plated along the top, so we had a failure there. Okay, so solutions to this. What do we do about this heat damage? And so what we have is we have quality rules for the copper thickness. We have quality rules for the amount of plating that has to wrap around a hole, because they have a process where they can grind it off, but if they don't leave enough, then you don't have enough strength. It's kind of like having not having a rivet where you should have a rivet. It doesn't have that wrap over plating. We have design rules for our hole size, for our pad size, the distance between holes. We have a lot of design rules that we've developed in order to maintain good quality. We also have a short list of laminates, these PCB laminates that we use. There's some that expand a lot. In fact, in this switch to the lead-free solder, it melts at a higher temperature, and we had to replace all of the laminates that we used in our circuit boards because the old stuff didn't work. It would fail because it expanded too much. So we had to evaluate for coefficient of thermal expansion, for temperature decomposition, and there were some other reliability factors. So we had to completely change over what our laminates that were used. So that was a lot of effort. And these do avoid failures in the majority of cases. I want to talk again, though, it's not just the swelling of the board during the soldering process where you go to 250C. And typically our board, because there's parts on two sides, plus it has through-hole parts, it goes through once for the bottom, once for the top, again for the through-hole parts. If you have a part you have to replace, that's a pretty significant part, you have to heat it up to take it off, you have to heat it up to put one back on. And all of those thermal cycles add to the damage that you have. and that can degrade the laminate also. Some of the vapors evaporate, and you end up with less laminate than you should have. It has more of a tendency to delaminate. So then you put it through on-off cycles during its whole life. You turn it on in the morning, you turn it off at night. Each one, maybe some of the circuitry gets hot during certain operations and then cools down. All of those small cycles also affect the reliability. So even if you didn't pre-stress by going through these thermal cycles for reflow and melting the solder, you could still have failures that occur if you have enough thermal cycles to stress those structures. So the question is, how many thermal cycles should a product survive? Okay, so this comes to the question of what is reliability. And here's a definition that I really appreciate. It's the ability to function as expected under the expected operating conditions for an expected time period without exceeding expected failure rates. So it's all about what the expectations are. For instance, our products, we have a 3-year warranty. They absolutely have to make it that far. We expect for ourselves that it lasts at least 7 years. But what we'd really like is for it to last as long as our customers would like them to last and how long they use them, which is more like 20. So we kind of have a balancing act of how long we expect them to last, because the more you have to put sometimes more effort into making them last for 20 years than it took to make them last for the 2 years that you might expect with a cell phone. So it's like for a cell phone where it lasts 2 years, probably everybody's happy with that. They want the new technology anyway, no big deal. And so they can cut back on some of the reliability factors, although there are some where they had failure modes that we didn't have, because if you drop your phone, you don't want it to break right away, right? And everybody drops their phone. And they actually found that they needed to make some changes in order to make them even last through a few drops. So just keep this in mind about expectations. And now I'm talking about a little life lesson. So the life failures that you can have of not being a good enough student, not being a good enough parent, not being a good enough, sibling, not being a good enough spouse, or a good enough worker at work. What's important is perfection is not required. Okay, you don't have to be perfect at everything. You don't have to be good at everything all at once. And I think that's something that I know a lot of us struggle with, is trying to be perfect at everything. It creates more stress than you need. So you need to have reasonable expectations for yourself, reasonable expectations for others. There's nothing that makes people more unhappy than to expect things of people that they really can't deliver. And I have this one a little more softly worded. Find a way for others to have reasonable expectations for you. A little easier with a spouse or a boss where you can have a direct conversation. A little harder with a father or mother or mother-in-law where it's a little harder to change their expectations for you. So if you can decide what's important in the moment and in the big picture, and do your best for what's important, and do good enough for the rest. You don't have to be perfect in everything. And when you get those moments playing in your head of all the stupid things you did, try to tell them to shut up. Let it go. You don't need to keep repeating that. It doesn't do anybody any good. And know that most of the time, you're doing okay. All right, so let's get back to the technical stuff. More failure types. So I talked about these laminates that we had to change them all so that they didn't expand as much in the z-axis. So what the manufacturers of laminates did is they changed the kind of epoxy cure. If anybody wants to know more about that, I can tell them. But there's more interlocking structures in the resin that keep it from expanding in that z-axis. The XY axis is a little bit constrained because of the glass weave, but z-axis not so much. And then some fillers that depress the coefficient of thermal expansion. So all of these really help to keep it from expanding too much. So that was great. We had lower z-axis expansion, fewer thermal failures, and we got boards that failed more easily from fracture. So that was a problem. So there was a new kind of defect called pad cratering, and if you were to drop one of our kind of products that's big and you had something that was fairly floppy, you could have this kind of failure. And I got sort of explain things. So this is another cross-section. This is another one of those balls in a ball grid array. So here's the solder, there's the copper pad on the board, this is the raw board itself. And there is a fracture in the laminate that was caused by a drop test that was done. So we do a test that basically makes sure that if the product falls off the truck, it won't die. So this was something that we found that for certain laminates, for certain kinds of ways that we had the parts on the board, we would have this kind of problem. So we have solutions to this too. So we have design rules for where you can locate these kind of vulnerable components. You don't want them in the middle of a trampoline. You don't want them where there's a fold line in the board. We have features that we can use to strengthen components at those kind of locations. And we also shortened our list of recommended laminates because there are some that were so prone to failure, we had to yank them off the list. Okay, another cross section. Again, we have component pad here. Here's the component itself. There's the PCB down here, another copper pad. Really, the colors don't come out very, or the gray tones don't come out very good. Here's the solder. So if you look at the solder here, it's mostly tin, and there are these little nodules of silver tin intermetallic. So IMC is intermetallic compound. So that's normal to have these little nodules in there. They're actually, there was an etch that was done. It's almost like they're leaves and other kinds of a different kind of look to them when you actually, than when you actually take a slice. But these actually, the silver is added to the tin. It lowers the melting point of the solder, so it's not so extremely high like pure tin would be. It also adds structural strength so that they actually survive a lot more in thermal cycling in the stresses that you can get. So it's actually a very good thing to have those silver. You get too much, it's probably bad because it'd be more brittle. They tend to be a little bit brittle. But this is what a normal solder joint looks like. That's what it's supposed to look like. So here we have, again, and again I'm prepping you for some of the other defects we can have. But this is a copper pad up here, component side. What makes a solder joint glue together is the formation of an intermetallic layer between the solder and the copper substrate. Or it could be between the solder and the nickel substrate. So what it forms is this little layer of tin copper right there, and that's what glues the two things together. You get the same thing on the other side. It has kind of these hills and valleys. It's supposed to have that. That's a good thing, actually. It's kind of a toothiness that helps it have some structural strength. If you have this too thick, it's actually kind of brittle. You've got to have some, but if it's too thick because of aging usually, then it will cause maybe some fractures, and that's why older stuff tends to break easier. So again, copper tin intermetallic. There's even some in the bulk solder, so this kind of hexagonal shaped thing is a nodule of copper tin, which is, again, no big deal. It's supposed to be there. And then the little things are silver tin intermetallics. Okay, so I'm going to go back a little bit now and talk about reliability evaluation methods. So when we're doing an experiment, we do what's the philosophy called design of experiments, where we have multiple variables that affect whatever we're trying to measure, and they're tested simultaneously. And in that way, you can figure out which are the major factors and what the interactions are, because in real life, almost everything has interactions. So you don't do a one variable at a time kind of test with this stuff. You've got to do multiple variables, have enough replicates so that you can actually make sense of it, but be able to test that versus each other. We also do thermal aging, so we don't want to know its lifetime or its ability to survive when it's young. We actually want to know out 7 years. If we age it 7 years and then do the testing, what is its reliability? So, and you can translate that to equivalent life with the normal kinds of temperatures that it would see. Then we do thermal cycling, and this is where we're trying to replicate the on-off cycles. And so we do that by extending the temperature range so that it still will give us the right kind of failure modes, but it makes it faster so that we get more strains and stresses on them. And then the ramp rates have to be carefully controlled, and also the dwell times are important for those failure mechanisms. But we don't want to have it stay at the high temperature for 8 hours like you would during a work day and have it cool down for 16 hours. That would take you forever to do a test. It would take you the full 7 years. So we have just enough time at each end of those cycles. And then you can compare lifetimes for different kinds of solder joints. And we also do mechanical stressing like vibration, bend, shock. We're trying to accelerate those failure modes that you'd see in real life, or sometimes just mimic them, like I talked about the test that's like the drop off the DHL truck kind of test. Okay, so I'm going to talk. I have to wave my arms a lot for this one. So when we showed that the circuit board's straining this way, right, during heat cycles, and that's in the on-off cycles, it'll do that too. But it also stretches this way. And so the plastic is stretching and swelling. The components typically have either silicon or ceramic in them, and they don't stretch and swell as much. Those have a lower CTE. So what you have is the component is stretching just a little bit with each on cycle. The board is stretching more. And so what those solder joints are doing is stretching out, and then they relax, and they go back, and they relax. And each time it stretches and relaxes, it changes the metallurgy a little bit. It changes what's happening in the grains of that solder joint. And so what you end up with is grain coarsening with each of those cycles, and eventually what you get is a ductile failure where it kind of rips and fails in that way. So here's a picture of a ductile failure. It's following the edges of the grain boundary. It's at the point of highest strain, which is over here. Usually on the component side is where it has the highest strain. And yeah, it's just ripped along there. So we'll find those, not as much in real life because of the testing we do, but that's what we're looking for when we're doing a reliability test for long life. We're trying to figure out which parts fail more faster in this kind of mode than in others. Okay, so other things. Gold is used to protect a nickel plating that's on a part, and it's very important. It's very good stuff, right? And so more gold is good? No, it is not. What we get from too much gold is more of this intermetallic. So this is, gold tin intermetallic is very brittle, and you get enough gold in a solder joint, you get these big plates that run through the solder joint, and you also get an accumulation of it over time. When we do aging, it starts to actually move. It moves down and settles along the surface there. And so what you get then is a tendency to crack either in shock or in thermal cycling. You'll get a tendency to crack along there. So you can see that this is followed along the gold tin intermetallic that accumulated at the surface. It's followed along a big grain, that a needle that went down this way, and then it followed another needle that went up there. So too much gold is not good. And it leads to a brittle failure as opposed to a ductile failure. It's very straight-edged kind of failure. It's not the kind of ripping, tearing kind of look to it. So a solution for that one, we specify a lower maximum gold thickness. And the other thing is that we do not specify nickel on one side. So if we have the availability of copper on one side of the joint, it actually prevents the accumulation at the surface, at the interface of this gold tin layer. And it helps you just a little bit in order to prevent the brittleness. So this one, it's an aged sample with the same amount of gold as this one, but with nickel on both sides, no copper available. And you have that gold tin layer at the interface. And then on this one, the gold tin layer didn't form. It's copper 6, tin 5, the copper tin intermetallic. And there's an awful lot of gold all the way through the joint, so that's not good. If you get too much, it's still bad. But you still don't end up with as high of a chance of that failing. Okay. And then this is another kind of failure mode. So this one was kind of odd. It was an unusual failure. I was called in to look at it. None of us could figure out what it was. The contract manufacturer couldn't figure it out. The component manufacturer, they were both blaming each other. We really had a serious issue, but what we found was a few things. So there's something it could be called non-wet, which when the ball went on the part to start with, it didn't ever make a metallurgical joint. So that's a possibility. But what we saw was that there is actually an intermetallic layer there. So it did make a metallurgical joint. There's another failure called ball drop, and that's when it's melted and it pulls away that you get it separating like we had in the pictures at the very beginning. But what we don't see here is you would have a meniscus of solder right along that pad, and we don't have that either. What we have here, what we can see on that side, is a fracture right through the intermetallic layer. So we had a joint, we had a failure, but it's a brittle failure that snapped through that joint. So the conclusion is it did not happen when it was melted. It happened just before it melted. So this fractured, and then the ball melted, and the solution was still the same. We changed the way we processed the board so that we wouldn't have this going through 2 repros. But it was, the main thing I want to stress is because it was from the warp of the part, there wasn't a lot we could do with it. We had to use the part, we had to use that board. What we could do was change the process. So we found a way to do that. And the other really important thing is it was collaborative. This was something that I guess I enjoy the most about my job is that I work with really smart people. And this was something where I had thrown this picture out for other nerdy people to look at. And somebody came back and said, you know, I think I might know what that is. Can I work with you on that? And I said, sure. I'd love you to work with me on that. And so he did a lot of the analysis, which, you know, doing cross sections like this, I don't know if you can see it, there's a lot of squares. So they did really in-depth cross sections, or SEM diagrams, micrographs of this, and mapped them all together. And so very complicated work. But they worked a lot on it, put I don't know how many hours on it. And then he says, you know, I'd like to pull in another friend of mine to work on this. And it's like, he mentioned the name, I'm like, oh, I know him. Yeah, I'd love for him to work on that. He's a metallurgist who understands what's going on here. And so he ended up also coming in on it, and they figured out what this mechanism was. Because it was something that was so unusual, I couldn't find any literature on it at all. There was nothing in the industry that had been written on it. So by collaborating together, we came up with the solution, or came up with what the cause was for this. We'd already developed the solution by knowing how to change the process to prevent this, but without understanding the root cause, it's very likely we could have had this come up again. So working together on that and figuring it out was very gratifying, and especially that working with very smart people. Okay, so a lot of our evaluations are done in collaboration with other companies through consortia, where it's groups of companies that have come together to work for a purpose. We have several that we belong to, and, well, I guess 3 that we belong to now. And very smart people, different people bring their different expertise to it. So like we have the metallurgist, we have the guy that can do the failure analysis, we have somebody else who understands about the processes. With all those people coming together, we can do a lot. And that comes to my other life lesson. So it's the last one. You don't have to do everything yourself. I mean, I think one of the things, you know, we have the failure to be, to achieve everything that we want, but doing it all yourself is really not necessary. I think it's important that we collaborate with helpful people. For one thing, you learn when you do that. The other thing is trust your spouse. A lot of you look too young for this, but when I had kids, my husband was one of the first people who really took paternity leave, and it was not really forbidden. It was just frowned upon. It was just the bosses were skeptical. But I think the important thing on that was that I could trust him, and I decided to trust him to take care of our children when I went back to work. And the thing with that is, rather than being a helper at the home, he was fully owned it. He fully knew how to take care of the kids. He was not, you know, oh, what do I need to do now? He knew completely what to do, and so that we could have that more equal partnership in the home. And I think that's very important to let go of the ownership of some of these things, so that it frees you up to play off each other's strengths and to be able to cover for the other when you're doing things, when you have other obligations that come up. And the other thing is trusting your kids. So that can be a little harder because it's an era of the helicopter parents, right, the hovering and making sure, I don't know if your parents did that, but you're making sure you're doing all your homework all the time and for one thing, we were never good at that. So, and for another thing, it was very contentious, especially with my daughter, you know, like at the screaming matches or whatever. So it's like, okay, fine, you do it yourself. You're responsible for it. And each of them in 5th grade got the phone call, you know, haven't been doing their homework. Like, okay, well, let's go have a meeting, let's talk about it. And what they learned is to own it themselves so that it actually helped develop their independence, which I think is one of the big things with raising children. I think it's important that you trust them enough to make some decisions and that they become independent humans. So, and the other is pay for services you hate to do, which is why we have a house cleaner, because neither one of us likes to do that. But there's probably more things I'd like to pay to do. But anyway, that is all I had for you. So thank you very much. Yes?
Can you give us an idea of how long these tests take? Because we are talking about the electrical, let's say, the mechanical, which has basically the temperature and also the shocks and the reliability. There are so many tests, so it's going to take a long, long time for an equipment like the spectrum analyzer, which is so big and so forth, to do all of these things before it gets out of the customer, the market.
Well, there's a certain number of tests that you do at the product level, and there's a few weeks of tests that are done there. There's for reliability, for the reliability of that specific product. There's testing that's done to make sure that it meets its specifications, and that can take from a couple hours to 24 hours to make sure every product meets its specifications. But before you even do that reliability testing of the product, you've done testing for the materials you're using and for the components you're using and all of that. And those tests take a lot longer. So as an example, one of the tests one of the collaborations that I've been part of is a test to do thermal cycling of different kinds of solder. So we use a solder called SAC 305. It's tin, silver, copper. It's a SAC. 305 is 3% silver and 0.5% copper. But there's 105 and there's 0307 and there's stuff doped with manganese and there's stuff doped with nickel. Or, there's a whole bunch of different things. And so there was a test done to test all of those. Try them out, a couple different part sizes, different temperature ranges. And that started 2010, I think, 2010. And there's one test that's still going because they used 1 hour dwells. Or no, the 2 hour dwell test, I think, is still going. So it's still percolating away. They're doing it to full failure of the sample size of 500. And it's still going because it takes a long time, especially for a part that's very robust. So if you really want good reliability data, you have to fail all of them. And so it can take years to get a test done. Now, some of them, like where we do a reasonable temperature span and 10-minute dwells, then you could probably get the test done in 6 months. It takes a long time. I mean, even that, it's kind of hard. You have a thermal chamber that's cranking away, going up and down and using energy both directions. Yeah. So it takes a long time.
But I bet you need to take this into the market. You may need to are you doing it maybe?
So that's independent. Those tests are independent of the specific product. So we do that before we choose a material. Okay? So we have to do those things before, like I would not choose one of those solders without seeing those test results. So the solder that we chose to use, somebody else was doing the test results, doing those testing, so we leverage that and say, okay, we can use this one. Somebody else comes out with a new solder, it's like, I'm not using it on my product until these tests have been done. And so it's always decoupled from the product itself.
And how long the product I think is going to take when we send it out, as I mentioned, the spectrum analyzer?
Well, we do all of our testing internally. So we can do the shock and vibe, and usually there's not a lot of temperature cycle testing. There's some. So it's maybe 6 weeks to get those tests done, maybe 8. Yeah. And there's a few things where it's cycling through temperature. They have to pass it hot and cold, and so they'll go through a few cycles of that kind of thing. And these drop tests and all of that, but we do it all internally. Yeah. Uh-huh.
So now that we're several years with experience with lead-free solders.
Yes.
How do they compare overall to the old lead tin?
In the thermal cycling test, consistently, no matter what the dwell time, which there was a controversy earlier, in this big test I was talking about, the tin lead always fails first,
Okay.
always. And so that is such a relief, because the idea was that this new solder, it could have a poorer life. I mean, we had 30, 40, 50 years, 60 maybe, years of experience with tin lead solder, and we had almost zero experience with the lead-free solder. But these tests have consistently shown that the tin lead fails first in doing these thermal cycle tests. It's more brittle, so that's like the cell phone folks. They went to a lower silver kind of alloy because it didn't fail as much when you dropped your phone, but it doesn't last as long in the thermal cycling. So silver adds some strength. So for our balance, it's better to have the longer life. Usually people aren't dropping our spectrum analyzers. So, yeah, hopefully not. So, yeah. Yeah, that's been a big relief. It's been over and over again in these tests.
Good, thank you.
Yeah.
Are those cycled to the same temperature?
Different temperatures. So like this test, 0 to 100, minus 25 to 140, a bunch of stuff in between, different dwell times, and every single test, the tin lead failed first. Yeah. Yes.
I have a couple of products where I don't like the SAC temperature, so I'm using bismuth alloy.
Oh, okay.
Very low melting. I've shipped a couple thousand over a couple of years now. I haven't had a failure yet, but I have no idea. Do you know how reliable, anything about the bismuth?
It's apparently weaker, so it doesn't have as much strength. Mechanically, yeah. I think for some of the other features is probably fine, but where it's the eutectic bismuth that's a very, very low temperature, one of the bigger concerns is that your operating temperature could get very close to the temperature, the melting temperature, and then it gets extremely weak. So like for ours, we expect it should run an ambient temperature of 55, and you have a 25 degrees C rise inside the product, so it's 80 degrees C, and it's maybe melting at 110 or something. It's getting too close. You're getting too close to the melting point, and the solder gets weak. So hopefully they keep working. I wouldn't use it. So.
These are all low power.
Oh, okay. Well, that's good. That's good. There's actually some new solders that are developing that don't have the silver to depress the melting point, but they use bismuth, and so they haven't been tested yet. So again, there's one of these projects going on in the consortium that's going to test these bismuth doped alloys that have like a reasonable, but it's more like 200 degrees melting rather than 212, whatever, and so, or 217. And so we're thinking, okay, well, let's see. That might be very beneficial for us, but we'll wait until we see the results of their long-term life. Any other questions? Yeah.
So what do you suggest in our case, right? Like right now, whatever we have are basically tin and lead based kind of solder, and whatever soldering irons we have are made for that particular temperature range.
Yeah.
So what do we have to do?
Well, if you're not shipping to the European Union, you don't have to switch, okay? Basically. So, but, so I would say carefully recycle your lead, be cautious about that so that it's not getting into the landfill. But, if you change, you have to get different soldering irons that have higher power because you have to pump more heat in. So it's not just a higher temperature, which you also need, but you need more power to continuously put that heat in there. So it would be a substantial investment to change for you. We already made that investment because we had to. So, any other questions?
About the copper thickness you talked about.
Yeah.
Some of these things, as soon as you want to do it, then there are so many things that comes in a given temperature and so on. There's the frequency, for example, and then also amount of current that's going to take and so forth. So what do you usually do in these cases? It's going to be very complicated because you need to have so many, things coming together.
Yeah. Actually, more copper is probably good for the electrical signals, and it's also good for the robustness of the circuit board. So when it's too thin and it's stretching, it's more likely to tear. So we actually want slightly thicker copper. But the other part of that balance is if it's thicker copper in that hole, it has to be thicker copper outside because you're plating it all at the same time. And when you have the thicker copper on the outside, you can't get your line widths as small because when you're making the line widths, you're etching in as far as you're etching down. So if you get too thick, you're also going to limit that trace and space that you can have on the outside. So there is a balance. I mean, we have a level we're using that is good enough. And if we get too thick, we might have problems on the outside as far as the line width that we need in order to make these complicated boards that need lots of traces. So, yeah.
Do you still have trouble with tin whisker growth, or is that a solved problem?
We have not seen any on our products. There are people that are still worried about it a lot. And so what this is, I left out that picture, so I was thinking about it. When you have stressed tin and pure tin, especially bright tin that is nice and shiny tin, it tends to be higher stress, and with that stress, it needs to relieve it. And the way it relieves it is one of the grains of tin starts extruding out a whisker, and it's like squeezing out a toothpaste out of a tube. It just keeps growing and growing and growing and growing and growing until it shorts something. So, and it's very thin, so usually after it's shorted, it burns away and you can't see it. It's very bad. We haven't seen that, but what we have is surface finish guidelines, and I think that those have been working. So there was, again, another consortium effort, a whole bunch of companies that got together and said, okay, these are the kinds of platings that work well, these are the kind that don't. And so we strictly adopt that, so our components, if they don't have the right kind of plating on them, we don't accept it or we recommend against or whatever. And that, as far as I can see, that's been successful. But those have been implicated, like in the Toyota unintended acceleration. Those assemblies had a lot of tin whiskers on them, and Toyota might have claimed that that wasn't the problem, and maybe not, but it certainly wasn't good. Probability analysis that was done showed that it could, cause about as many unintended accelerations as we actually had with that. But, you're ending up shorting something that should not be shorted. And so it's a very serious problem. Yeah, and especially in space and in vacuum is where they tend to grow even more so. So the space people are very adamant about not having pure tin coatings. But we haven't really had that problem. Thank goodness. Yes?
A lot of these things that you are talking about are really important. I bet you push these things, your testing and so on, to the, shall we say, standards organization. What are the main standard organization for this type of reliability of that? And then, and also, temperature, there are all sorts of things. Where do you usually,
Push those standards?
Push the standards, yeah.
So IPC is an organization that is the main standard creation body. And they partner with JEDEC, which is the other one, so JEDEC. And so between those two, they have standards for all sorts of things. So IPC has workmanship standards and some design standards. Some we adopt almost whole. Other things we develop our own because theirs are too general. JEDEC has like the testing standards for how you do thermal cycle testing and how you do some of these other tests. So so they have committees that develop the standards. I was on one for pad cratering standard because there's actually no good way to determine the susceptibility of a laminate to pad cratering. There's just not a good method yet, and so we've been working on some different things. People have been trying stuff, and there's been some methods that are documented, and I think they still need a little more time before they're well proven. But any of the other things that where we need a new standard, that's where we would go to actually get it put into the standard. But the other consortia that do the testing to develop the material that would drive you to changing the standard, there's one called HDP users group, so high density packaging users group. They do a lot of good work. And then another one called INEMI, which is the International Electronic Manufacturers Initiative. And there's projects in there, again, multiple companies that get together and do a bunch of work that then go into the standards. Yeah. Other questions? Yeah.
We're talking about multi-layered PCBs. What's like the average number of layers, and is there like a threshold where you shouldn't go?
We have, like 12 layers is actually really common now. Like 5 years ago, I might have said 8. I've seen as high as 26 that we use. So that's, at some point you're getting either really thick, which means it's harder to drill the holes and harder to get plating in the holes, or you're getting really thin layers, which can cause some shorting between the layers, that kind of problem. But there are some organizations that have like 100-layer boards. So they get what I think is maybe a little extreme, but it can be done. Yeah. Yeah.
All right, it's now close to 5:50. I'd like to thank Julie for giving us such an interesting talk, which in fact gave us a lot of insights, practical insights about the products, which are so complex and so on. And then you as electronic engineers, I think you can see now how things go, and then suddenly go to other areas which would be very difficult to work with, and then we need to work in fact with others to make it happen. So let's thank it again.